Okay, good morning and welcome back to our third lecture now. We begin today uh, really the hardcore of the course. In the previous lectures, we've been sort of setting the stage for all the topics that will be covered in the course. First, we revisited the concept of physical modeling within the framework of modern renormalization group theory. Next, we developed some technical skill. In particular, we familiarized a little bit with the formalism of path integration and functional formalism, which is a main tool that will be used in the remaining of these lectures extensively. Now it's time to go to the heart of the course. And the heart of the course, like I discussed in the introductory meeting we had, is about dynamics in open complex systems. In many ways, they can be classical or quantum, and they have to be complex in the sense that in general they would be non-perturbative with non-linear effects being involved. So today we begin this journey, and we started from the simple possible framework, which is a classical framework. So I would say this is the beginning of the journey on dynamics in open systems. And again, open system is a system that is not isolated from the rest of the universe in some adiabatic box, and therefore not exchanging energy nor any conserved quantity with the external world. We are used to working with closed systems from the beginning of our physics education, basically. And when we write the Schrödinger equation, we have in mind the Hamiltonian for a particle or a systems of particles, and we don't consider anything else in the universe. There is no such a thing as an isolated system in the universe, if you think about it, but it's an approximation with which we use almost always, at least in our education, to neglect whatever happens to anything else other than the particles we write down in the Hamiltonian. But there are many situations in which this is actually not possible, and the simplest one being when you have a bunch of particles that are in contact with a heat bath. Think about the macromolecule in a solvent, and say trivially water, which could be, I don't know, a protein in the cell. The protein is obviously not an isolated system, it is interacting with the environment. But even quantum bits in a quantum computer have to take into account of the fact that a quantum computer is operating at a given temperature, it's in an environment, and this is a source of errors and stuff. So there is quite a considerable growth in the attention in the scientific community towards developing methods to systematically accounting for the fact that the system is being open and it can interact and exchanging basically energy, angular momentum, linear momentum, or whatever physical quantity with an environment. And in some case, the interaction with the environment is absolutely crucial, like in the case of physics of living system. Without an environment, there's going to be no life. Okay, so one of the things we're used since the very beginning of our education is that when the system is open, typically we face phenomena such as the growth of entropy, which we formulate usually through the second principle of thermodynamics. And the most simple example being, the gas expanding in a box and blah, blah, blah. But we know from our previous education that the growth of entropy is usually associated with irreversible phenomena. If we are in a reversible, perfectly reversible system in vacuum, then I have a ball bouncing on the floor. Suppose you have a perfect basketball bouncing on the floor, and there's no air, and there's no sound propagating, and the ball is perfectly elastic. Suppose I take pictures of this, and I put them in a series at different time, and I'm asking you, can you please tell me can you put these pictures in order, in time order? Now, of course, you cannot, because there's no particular way to say that this is coming after this picture, this frame, because this could be a previous position of the ball, or could be a later position of the ball after bouncing back on the floor. So when you have a closed system, you have energy conserving dynamics to begin with, there's no time irreversibility, and there's no way to direct the arrow of time in any ways. But we all know that if we throw a real basketball on the floor and wait for a couple of seconds, maybe 10 seconds, depending on how good is the floor, how good is the ball, then we discover the ball is sticking to the floor. And the reason we know is coming from the fact that the ball has exchanges energy with the environment by, first of all, moving air molecules as it's going down. There's some intrinsic friction. But then even when the ball bounces on the floor, it generates oscillations on the floor, and in turn the oscillation of the floor puts the air around the floor in oscillation. And this is responsible for acoustic waves which carry energy and carry energy away from the ball. Now, if you were extremely careful in accounting for all the energy balance in the room, assuming adiabatic walls around the room, then you will claim, fine, first principle of thermodynamics says no energy is being destroyed. If I really can account for all the energies going into the air, which has slightly increased its temperature, and into a acoustic wave, which also led to an increase of temperature in the room, then basically nothing changed. However, this energy is now distributed in a very large, astronomically large number of particles, many orders of magnitude larger than the Avogadro number, because for each cubic centimeter of air in the room there is an Avogadro number of air particles, roughly speaking. And so basically the chance for all this energy to go back on the ball is exponentially small in the number of particles, and that's the origin of microscopic irreversibility. I would say this is more or less what we learned second year or first year in physics education. The question I'd like to address now is, okay, fine, that's good from a macroscopic point of view, but can we go down on a microscopic point of view and see how on Earth, starting from a Hamiltonian description of my system, which is explicitly energy conserving and time reversible because it contains two derivatives. The equations of motion are second order to time equations of motion, so if you perform a reversion of time, well, this reversion of time is cancelled out in the second derivative. How on earth does it happen that my resulting dynamics is friction affected and therefore irreversible? In other words, how can we monitor exactly in a line of an equation when you're beginning to see the effects of the arrow of time? So what we're going to dig in the next few lectures is origin of the arrow of time, starting from a full Hamiltonian perspective. And I will add another topic which is perhaps less particularly transparent at this level, but will become transparent quite soon, and is origin of stochastic behavior. Well, we all know classical mechanics and Hamilton's equations are deterministic equations. We all know that given an initial condition, there is only one trajectory in phase space crossing that initial condition. Yet we all know we cannot trust weather forecasts for more than a couple of days. So we know there's some stochastic in her, and we know that weather forecasts obey the classical laws of motion. So we all know that the deterministic character of classical mechanics is an illusion. And in reality, as soon as the system gets slightly more complicated than a ball rolling down a linear plane, then things become stochastic. And we would like to understand, number one, what happens and why it becomes stochastic, what is the origin of this stochastic behavior, And number two, find convenient ways of accounting for this stochasticity in a way that doesn't spoil the usefulness of the theory. And this will lead us to define what is called stochastic dynamics. Okay, enough for chit-chatting, and it's time to sort of begin our journey. And so let's consider a system that is, let's consider specifically a Hamiltonian system. And our system will therefore be defined by a classical Hamiltonian for the moment. We will deal with the quantum extension of this discussion later on in the course, when we will discuss quantum open systems. But for the time being, let's stick to the classical regime. We have our nice and beloved Hamilton's equations. I was actually writing down. And the second equation is obviously Newton's equation. The first equation is just a definition of velocity given the momentum. Okay, we know that, if I work in phase space, and I will consider phase space for the sake of simplicity here in just one-dimensional system composed by one single particle, but everything can be generated with an arbitrary number of dimensions and an arbitrary number of particles. Just the possibility of drawing pictures will be compromised beyond the simple limit we are considering, because I would need 6 n-dimensional graphs to represent the dynamics. So if you stick to one particle, 1D, then I can put, as usual, momenta here, and that's the phase space. And I know that I can draw a point in phase space. Let me write it this way. And I know that there's only, given a point in phase space, there's only one trajectory which can be generated by integrating the Hamilton's equation forward or backward in time, starting from this initial condition. And therefore, we know the Hamiltonian trajectories basically never cross. Because if I were in this point, then this unicity Cauchy theorem would break down. So that's determinism. That's classical determinism. Notwithstanding all the features associated with chaoticity, which is a delicate issue, and I will not go into the Lyapunov exponents at the moment. I leave this to the previous courses in analytic mechanics. We know that in order to have one trajectory, and only one, we need to have infinite information about the initial condition. Because if I start from a slightly different initial condition, then of course I will have, at least for a short time, a slightly different trajectory, and then maybe the trajectory will become exponentially, the trajectory will become exponentially distant from my previous trajectory if there is a Lyapunov exponent. But in either cases, the difference of initial condition will produce a difference in the final condition at time t. Okay, but we know also from the first lectures in this course that no experiment will ever have a resolution to define the point in phase space, because defining a point in phase space requires infinite accuracy. Okay? Defining a point in phase space requires infinite accuracy, and no experiments can claim an infinite resolution. But even if we did not matter about this, we would have the problem that the system is often full of uncontrollable variables. Think about a protein in an environment. There's no way you can fix all the positions and velocities of all the water molecules in your box. So even notwithstanding these RG arguments about resolution, there is basically no way you can control all the variables in the system. So when you cannot control the variables in the system, you don't really know your initial condition. And so you basically have a cloud of possible initial conditions. So you can define this lack of knowledge by giving up saying that initial condition is a delta function in phase space, and instead assume that your initial condition, you can define the probability of phase space in time t. That's the starting point of classical statistical mechanics, and that's what basically you have seen already in the third year when you began your introduction to classical statistical mechanics. But what I'm trying to say here is that your probability density is whatever is left after you accept the impossibility of fully determining your classical system with infinite accuracy. And basically the problem of solving Hamiltonian dynamics is the problem of solving for the probability density in phase space at time t given the probability density f ton t naught. So even in classical mechanics, we are left with a problem that is very similar, at least conceptually, to a quantum problem, where we were having, say, an initial wave function, and we were interested in solving for a final wave function after some time. Well, actually, say the initial probability and final probability. Now, gamma here is a point in phase space. I should have probably said that. So classical and quantum mechanics looked very different when you look at closed systems and one particle, and you don't care, and you assume you can actually determine the initial conditions with infinite accuracy, but they actually are extremely less different, much less different if you look at a realistic situation where you have uncontrolled variable and you're not able to completely determine the evolution of a system. And if you stick to the Hamiltonian system, all you want to do basically in a complex environment is understanding the evolution probability in phase space. So what you want to find is a partial differential equation that evolves your state density in phase space in time, enabling you to understand how this probability evolves. Just as much on the same footing as in the quantum mechanics when you finally arrive to the Schrödinger equation. So probably most of you already know the answer. What is the equation that dictates the evolution of a probability density in phase space? It's the Liouville's equation. But let's go over it anyway, just to fix things and be all on the same page. So, of the equation that governs the time evolution of the phase space distribution is well known as the Liouville's equation. And this is a typical topic for the introductory course in statistical mechanics, and I will not deal with this derivation at the moment in great detail. Just remind you that the way it is done is by considering a small volume of dq, dp, phase space, and then looking how the total number of microstates in this small volume evolves with time, and then basically counting how much flows in and how much flows out. You arrive to an equation that normally can be written in the following way. That's the famous Liouville's equation. And I will now restore provisorily the number of particles, although we discussed that we are facing the case specifically of a single particle. That's it. Let's do the following. D by dqi p pi equal naught, which can be written in the famous compact form for Hamiltonian system expressing the null variation of the total probability density uh, which expresses basically that the Hamiltonian evolution behaves like an ideal uncompressible fluid in phase space. This is all well known for statistical mechanics. What I would like to do here is simply to notice that still for a Hamiltonian system, this equation can be written in a form that is even more reminiscent of quantum mechanics, because it can be recast in the language of Poisson brackets in the following form. But these are Poisson brackets. And this is an expression that really is reminiscent of Heisenberg equations of motion. And in fact, you can derive from that the evolution of observables that depend on phase-space variables that really looks like a Heisenberg equation, with the only difference of replacing commutator with Poisson bracket quantities. So again, it's trying to even further establish a connection between classical mechanics and quantum mechanics. You can rewrite Liouville's equation in the following form. Where L is the Liouville operator defined in the following way. That's again restoring momentarily a variable number of more than one particles, just for sake of notation and completeness. So in this language, we see there's a very close connection between whatever we saw in classical mechanics and quantum mechanics. Now, there is a fundamental difference though. Quantum mechanics is intrinsically uncertain because of quantum fluctuations, regardless of having a closed or an open system, regardless of having complete knowledge of the system. While classical mechanics is uncertainty, the uncertainty in classical mechanics is just a consequence of the fact that we don't have complete knowledge on the system. But again, if we believe we never can have complete knowledge on the system because we can only resolve experimentally a finite amount of information, then we are still back on the same basically unavoidable concept that we do not have determinism in physics. Whether we are at a macroscopic scale where we can apply Liouville's equation, or we are at a microscopic scale where we have to use Schrödinger equation, or it's even more microscopic variants that occur at large energies. Very well, so that's the state of the art, and in principle, therefore, our problem is still that of describing the evolution of a system through a partial differential equation in a large number of variables. And in some sense, this is probably the connection that we are outlining in this lecture is probably the reason why Einstein never believed in quantum mechanics being a fundamental theory, because he knew from his understanding of stochastic behaviors in classical mechanics that stochasticity is often the result of missing variables or missing information, and he said, no, quantum mechanics is it has a stochastic nature because we are probably not able to resolve some underlying microscopic variables, and that's the result. We know today that this is not the case, in the sense that quantum mechanics is much more than simply missing variables, because it has all this phase information and Bell inequalities and all this entanglement business that we have learned to appreciate and validate experimentally over the last several decades. Notwithstanding this, this is a very important analogy to live with. So now, having said that, let's move forward and say, okay, now what happens? Well, this equation, solving Liouville's equation, is really like not workable in practice for almost all possible situations you might encounter in real life. It's an important theoretical statement to draw general conclusions in statistical mechanics, and it is used in derivations of several results in statistical mechanics. But as far as solving the system is concerned, this is not certainly the way to go. And so how can we account from uncertainty and stochasticity without having to solve the Schrödinger, the Liouville's equation? So how can we practically account for incomplete knowledge? My hand script is getting worse by the day. Incomplete knowledge and stochastic behavior without, let me continue here, without having to solve Liouville's equations. That's a question we want to answer. And by trying to answer this question, we will also address the question that I stated at the beginning of the course, that is, what is the origin of the arrow of time? And let me anticipate that the result, the key word that will emerge by trying to answer this question is the concept of stochastic equations of motions. Okay, so in this lecture, we will begin deriving the stochastic equation of motion, starting from non-stochastic equation of motion, that is the Hamiltonian formalism. So what I will be discussing now is some practical variant of a general statistical mechanics theorem, relatively recent, is in the late 60s, was proven by Mr. Zwanzig, and it's called the Moritz-Zwanzig projection formalism. Now, in my notes online, you can get the derivation of the Moritz-Zwanzig projection formalism. Zwanzig. Let me check the spelling of it, actually. Zwanzig, it was correct. I was just Zwanzig. If you look at the notes on my webpage, you get the formal derivation of the Moritz-Zwanzig theorem in the most general case. Unfortunately, that derivation is not particularly physically transparent, nor it is useful for practical applications. So for the sake of didactical purposes, I prefer in this course to explicitly provide an implementation of the projection formalism in a simple case, in the simplest possible case. And this exercise would be far more reaching in terms of physical transparency. It will allow us to make to see in phase what happens when you have an open system, much more than we have if we define projection operator or Hamiltonian dynamics or things like this. So let's be specific and consider a system consisting of defined by Hamiltonian, and we arbitrarily split the system in two parts. We have a system consisting for a moment of one particle in one dimension, like I said, but here you can restore n particles in n dimension. That's an unnecessary complicancy for the time being, plus an environment. And we will assume that that's the model, an environment consisting of a collection of harmonic oscillators. Now, obviously, You need to couple the harmonic oscillator to your system, or else they will remain just two independent worlds. Okay, let me put a summation here and a parenthesis here. So now you see, this is my system. I would call it the system. It's a subset of variables in my Hamiltonian, and this subset of variables, x, is also linearly coupled to a collection of harmonic oscillators, each of which has its own mass mu alpha and its own frequency omega alpha, and there is a coupling constant between the two that is dictated by this C alpha. So it's really like if I take in my particle and I'm attaching to it a bunch of harmonic oscillator. Plus the particle can interact with an external potential. Now if your particle instead is a collection of particles and this is a point configuration space, then you have an internal potential, and these harmonic oscillators will just determine the interaction of the system with an environment. So this is often called in the literature the Caldeira-Leggett model. And it's useful because we will revisit that also in the context of quantum mechanics. Before we get started, let me immediately ask a question: how relevant is a problem like this? I mean, how often do we see particles attached to a spring in real life? And the answer, of course, is very rarely in real physical problems. So one would be probably inclined to thinking that this model is just a toy model with basically no practical applications. It turns out it is not the case, because under certain situations in which we will be dealing with in a moment, we will make use of this renormalization group idea, according to which the details of ultraviolet coupling in physics is irrelevant, so we can choose any essentially model we want. And therefore, we will be able to study the implication of ultraviolet coupling to soft dynamics using this model. But we will come to that. At the moment, I don't expect the physical relevance of this model to be immediately transparent. We'll come back to that later on. So the idea here is to solve this model, integrate out the variable in the bath, and see what happens to the dynamics of the system. That's the concept of incomplete knowledge right there. So how do we do that? Well, of course, we do that by writing the equations of motion. So the equations of motion of the system are, of course, the Hamilton's equation for the system. And let me write it this way. There's a linear coupling, so we see the coupling constant popping up here. And there's, of course, the equations of motion for the bath. Let me stress once again, here and here, we see how the bath and the systems are coupled. So, okay, so we have our theory. In principle, we would like to solve for this theory. And in general, solving for a coupled differential equation problem is horribly complicated, because the problem of coupling differential equations is that, say, if you want to solve for this problem, you need to have the solution of this problem. But if you want to get the solution of this problem, you need the solution of the previous problem. That's the concept of coupled differential equation, and that's why they are so hard to solve. But in this specific case of harmonic system, you can get around to this problem. And that's why we choose this simple model, because in this very simple case, you can actually solve for the entire problem. So let's focus on the bath problem first, because that's the system consisting of linear it's a linear problem of harmonic oscillator linearly coupled to my system variables. So let me just erase this to make it more visible. You see, the main point to be stressed here is that this is a linear equation. And it contains my variables, and it contains a source term. So if I look at it from the point of view of a differential equation, this is the problem of solving a differential equation for my bath variable in the presence of a source term, x, c alpha, which is due to the solution of the previous problem. So how do we solve differential equations which are non-homogeneous? We find the most general solution of the homogeneous problem, and then we add one specific solution of the inhomogeneous problem. We know that from our first or second year in calculus, depending on how the didactic is organized. So, to solve for the bath, let's solve the homogeneous problem. Well, the homogeneous problem is basically the problem of harmonic oscillators. So we know the solution. They're just harmonic oscillators. So we know that in the homogeneous case, the Q alpha can be written by solving Newton's equation for the harmonic oscillator, neglecting the coupling to the system. That's the concept of homogeneous. Now, what you see here, these are the famous initial conditions in your Cauchy problem. Let me write this in the second line. These are basically the initial conditions in the second problem, in my bath problem. And the way you fix them is as usual. You get the general solution, and then you impose the initial condition, and you fix the A and B constants that would appear here. And I will not go through that because it's really, 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 really very, very standard. Now, in order to get the general solution of the inhomogeneous problem, we must find a specific solution, one specific solution of the homogeneous problem. So, general solution of the homogeneous problem plus one specific solution of the inhomogeneous problem will provide a complete solution of the problem. So the next step is actually find one specific solution of the inhomogeneous problem. Specific solution. Okay. Okay, let's look at the problem then. The problem for which we want to find one solution is in order. It's Newton's equations for my bath variable. That's the harmonic oscillator part, which we don't get surprised. And then there's, of course, the coupling with the bath system. Now here comes the advantage of having a linear system. I can Fourier transform this equation in omega space, in Fourier space, and I get the following equation. Okay. What I see here, these are, oh, actually this is not visible. Let me copy this downstairs. This is my Fourier transform of my path dynamics, my systems dynamics. Now, what I see here is the advantage of linearly coupled. Because if I didn't have a linear coupled between my path and my system, I could not be able to write this equation as simply a collection of Fourier transform, because the Fourier transform is linear only if you have Fourier transform of a sum of function is the sum of Fourier transform of functions. But if you have Fourier transform of a product of function, that would be a convolution. So if instead of a linear coupling here, I would have a quadratic coupling, then this expression here would be much more difficult, much more involved, and it would not correspond simply to a sum of Fourier transforms. But since, and likewise, if my path was not composed of a linear system, then I would have not been able to write this part of the equation in the simple form, because the equation of motion would have not been linear once again. But since I have done this, then I can solve this for QA, because this is just a polynomial equation of first order in Q tilde. So I can solve this in a trivial way, and I will get the following result. Okay. Now I have the Fourier transform. I can go back and evaluate the position, the solution in time representation simply by anti-Fourier transform. So I can write the following expression. What is this? This is expression obtained by anti-Fourier transform this product of function, which contains a kernel and my source term. And the anti-Fourier transform of this is a convolution. And the convolution is the anti-Fourier transform of the kernel times the anti-Fourier transform of my function. And the kernel can be written explicitly in the following way. And let me write it in Fourier space. So basically what this is written here is I'm trying to anti-Fourier transform this function here that enters here. So let me just isolate this. It's like 1 over omega alpha squared minus omega. And I want to evaluate the anti-Fourier transform of this object. And I'm facing exactly the same problem that you face in quantum field theory when you want to evaluate quantum propagator, say, the Klein-Gordon field. You want to perform this anti-Fourier transform. This anti-Fourier transform of this function as a pole cannot be defined in terms of a function. You need to define it in terms of a distribution. And you define it in terms of a distribution by shifting the pole slightly by an infinitely small amount onto the complex axis with a convention. In this case, you shift the pole in one way on the complex plane. And the reason you choose this sign, and then you let this becoming a distribution, and at the end of the calculation you're supposed to choose epsilon very small. So that's the concept basically of standard distribution representation of delta function, for instance, for the Sobchakov formulas, I think they're called, or whatever they are. And why do I choose the plus sign here in this particular formula? Because this integral can be done analytically 1 second. This function can be done analytically and corresponds to the following expression. Now, this delta function comes from the right sign of this epsilon term, which basically, you can fix it a posteriori by imposing that the motion of the particle at time t can only affect the bath dynamics at a later time. So this is a causality request. Or principle. If you had chosen an opposite sign, we would have had the opposite causality. Only the past can be influenced by the future, which is obviously not what we experience in real life. Only the future is influenced by the past. So, by this I epsilon, we are basically imposing a causality in the dynamics. And there's no antiparticle, there's no weird phenomena here that might mix up with causality. So we know that we are time directing in the sense that whatever happens now will influence the future and not vice versa. Okay, now all we can do is to combine this homogeneous and inhomogeneous term and get a solution for my bath system. Okay, plus the inhomogeneous term. Okay, so now we have a solution for the bath dynamics, given the solution of the systems dynamics. Fantastic. Which means that now we can plug this back into the equation for the systems dynamics and get the closed equations for the systems dynamics. That's the advantage of having a linear coupling and harmonic oscillator. So now I can plug this back and get a Newton's equation, or Hamilton's equations, for the x variable, which explicitly depends only on the initial condition of the q variables and on the x dynamics itself. So let me write this equation in the following form. That's the Newton's part, that's the part we had before. And then the part that was originated by the linear coupling with the harmonic oscillator, given that we know the solution of the linear coupling as a function of x itself, becomes the following. Cos omega alpha t minus s, and then there is a term minus x of t plus some terms f of t that we'll discuss in a minute. And this term f of t, I guess it's just simply sum over alpha c alpha q alpha of t naught cosine omega alpha t minus t naught plus E alpha naught divided by mu alpha omega alpha sine omega alpha t minus t naught. Okay, so I have a modified equation of motion. Modified equation of motion. This is the closed system dynamics. And these ones here are the implications of the open system dynamics. And I want to emphasize one thing. Let's look at this term F here. Well, this term is a force that depends on the initial condition of the bath. So given, if I knew exactly the initial condition of the bath, the value of any of these components, I'm plotting different frequencies here, and then you would have to add them all. So you see, given the frequencies of the harmonic oscillator, given the initial condition, then you have to sum all of these harmonic terms in order to get this force. And sometimes you get the positive sum, sometimes you get the negative sum, then there would be, but if I sum all of them, I will get a very, very complicated expression. But now comes the point. At this point, we should remind ourselves that we do not know all the initial conditions. So basically, since we do not know these initial conditions, these terms here will behave as stochastic variables with a given error. And what happens when you sum many stochastic variables with alternating sign? Well, the central limit theorem tells me you get a Gaussian. However, there will be some memory effect, you see. Depending on the frequency you have on this expression, you will be sensitive to the value of the initial value of your correlation for a finite amount of time, of your bath variable for a finite amount of time. If omega is 0, very, very soft frequencies will retain the value for a very, very long time, as a result of which the stochastic behavior would be simply the force at time t will be dictated by the initial value of my initial condition, which is unknown. In the opposite limit, in which all the frequencies of the harmonic oscillator are extremely fast, then they do behave like independent stochastic variables, leading to a Gaussian distribution, basically, with zero memory. Because you have so many fast oscillations of different frequencies that for any significant difference in time scales, then you're completely uncorrelated. You have done so many oscillations that you lost track of whatever happened at time 0. So we're beginning to see again RG concepts popping at us. We're beginning to see this some quite a striking effect that depending whether you're in a regime or in another in terms of timescales, then we do get different behavior. So the way to rewrite this equation, the way it is normally rewritten, in the following compact expression. This is the Newton's part of the equations of motion. This is actually supposed to be x in my terrible handwriting. And then I have a term which I'm going to rewrite for convenience in the following form. Here I have a canal, I have my x dot at time s plus some terms psi of t. Now, this term here reads as follows. Well, not surprisingly, it is proportional to the coupling. Now, it is interesting to look at this term, and the first thing what comes to the mind is that this term actually provides a generalized type of viscosity interaction. So a single time derivative has appeared in the game as a result of integrating many Bath variables. Single time derivative means that time reflection invariance has been lost. So the equations of motion are no longer even under flipping of the time arrow. A well-defined time direction has come because this is an even function, but this is a not function of time. So you see, the explicit integration of the time variables has produced the breaking of Z2 group time parity in the equation through an explicitly viscous term, so dissipative term. That's how dissipation emerges from a microscopic point of view in this model. Psi of t, if you write it explicitly, can be written is my previous f of t minus mkt minus t naught x t naught. So this term here is basically a rescaling of the force that I was writing in the previous board expression. And again, this term has the interpretation of a stochastic force. Stochastic in the sense that any small variation in the initial condition propagated over time, if the frequencies of the oscillations are sufficiently fast, will result basically in a Gaussian type of stochastic noise at time t. So this is the so-called memory kernel and it's associated to viscosity or dissipation. And this is a stochastic term and it's associated to fluctuations. So in other words, this equation is telling me that every so often my particle gets a random kick from the harmonic oscillator, and every time it dissipates some of its velocity and momentum, therefore energy, to the oscillator through this term. These kernels here tell me that the effect between the kicks, the fluctuation in the bath, and the dynamics of the particle are generally occurring after some characteristic lag time that is controlled by the frequencies of the harmonic oscillators. So up to this point we made no approximation whatsoever given the model we started off with. We're still completely general, and of course I have to convince you that that model is irrelevant at all for physics, but given that, we're still completely general. It is convenient to relook, so since in both expressions the kernel plays a crucial role, and it's the role of determining the gap, the lag time between any fluctuation in the bath, the time it takes for this fluctuation in the bath to propagate and determine a change in the dynamics in the system, it's convenient to look at that a little bit further, and so we do so by going into frequency space. So if I look at the Fourier transform again of the kernel, well, it looks the following. So what you can see here, the prefactor essentially determines the strength of the coupling of these fluctuations to the particle through this coupling constant. And the second term is essentially a spectral density of fluctuation in the bath, because it has a collection, is a comb of delta functions, one at which characteristic frequency of my harmonic oscillator. So if I had a discrete system of harmonic oscillator, this would be like a set of frequencies, each of which with a strength given by the prefactor. Now we know delta functions are not really finite height objects, but when you smear them, then of course they have a finite height, and the proportionality between relative proportionality of these smear delta functions is given precisely by this factor here. So this is really the strength of a given mode into the spectral density, coupling strength. Now let's now make the limit in which I'm using infinitely many harmonic oscillators. Then clearly in this infinite limit, where the number of particles in the bath is much larger than one, much larger than the particle in the system, then I have a spectral density. It's an even function with a spectral density. And I'm not even quite sure. Well, that's the frequency, that's k over omega. Now, for the time being, I was passing through zero. That's not necessarily the case. Some kind of a frequency. Now, it's time to make assumptions. And the assumptions we're making is the RG assumption. Once again, renormalization group-based assumption. I'm saying, let's assume that all the omegas are much larger than the typical omega that enters in the Fourier transform of the particle's dynamics. In other words, we are assuming a gap in timescales between the typical timescale, inverse timescales where the system changes its configurations, and we are assuming that most of the frequency of the harmonic oscillators are picked around higher values. What would that mean? It means once again that I can Taylor expand my spectral density k omega as a constant term plus I omega minus omega naught c naught blah blah blah. And omega naught is 0. So I get a constant term plus a frequency term plus blah blah blah. Now notice that this time, unlike in the example we did at the beginning of the course, I am not prohibiting the lowest order in omega, because we know that there is time irreversibility now because of this velocity term. So now I can allow for terms that break the irreversible character of the dynamics, the reversible character of the dynamics, because the dynamics is actually become irreversible because of the emergence of a viscosity term. Now if I back anti-Fourier transform, I get an explicit expression in this limit for the kernel. If I only retain this, I get that this is basically, this is a C naught, of course, as a coefficient. And if I back Fourier transform this, I get C naught delta of t minus s. Likewise, in the same limit in which I decouple the high frequency modes from the slow frequency modes of the system, even the stochastic force becomes delta correlated, which means that the correlation function between the force at two subsequent time are 0 unless the times are within the cutoff of the theory. So basically within the smearing of the delta function, which means essentially that any finite amount of time relative to the dynamics of the slow particle, within any of these time intervals which are small in the dynamics of the system, the stochastic force changes by a random amount, losing memory of the previous value. So this together means the following, that the k of t minus s can be written as a delta function of t minus s times a constant, and for reason that will become clear later, let me call this constant 2 gamma. So with this equation, the stochastic equation, the equations of motions for my particle becomes p dot equal negative gradient of u. Now we get a term that is a classically well understood viscosity term, x naught, plus this stochastic force T. Now this stochastic force T has the given expression that I was referring to before, which is what it is. Depends on the initial condition only. And if you make the assumption of this, it's a number that only depends on the initial condition. Remember, if you rewind your expression by a couple of pages, you'll discover that we provided you with an explicit expression of psi of t in terms of f of t and the kernel. Now we come back, and these terms here depends on the initial condition p alpha 0 and q alpha 0, which you don't know. Now, one thing you always do when you don't know, you marginalize. What do I mean? We don't know the initial conditions, so we make an assumption. We assume the initial conditions are at the moment when I start my simulation, the system around the particle had the time to thermalize around it. So that means that the distribution of initial condition of p alpha at time t naught, q alpha at time t naught, given the position x at time t naught, was actually Boltzmann. And Boltzmann means I don't have room here to write. Let me just say it is something like 1 constant time, and I can write this as minus 1 over kt alpha p alpha squared naught divided by mu alpha plus 1/2 2 mu alpha 1/2 omega alpha square mu alpha times q alpha square t naught negative x with some constants, c alpha, mu alpha, omega alpha. Okay, given this, what you do, you perform a Boltzmann average over the initial condition. And if you do that, you get out important properties for the xc functions. Basically, your resulting c is the result of the expression that we wrote after you integrate over the initial condition assumed to be Boltzmann distribution. And if you do that, you can easily do that because the expression becomes simple given the kernel which assumes a delta function relationship. And what you find is the following part. First, you find that your stochastic force has zero average at time t, and then you find the following important relationship. Okay, so these two relationships are fundamentally important because they tell you that the stochastic force has zero average. That's what you expect because they get kicks in all directions. But they are delta correlated. Let me write the delta function downstairs here. But most importantly, the strength, the variance of the kicks you get from the environment depend on the temperature and on the viscosity. So there is a relationship between how much energy you get from the environment through the thermal kicks and the energy you dissipate into the environment. So in other words, what we are discovering is a fundamental equation in physics not fundamental actually, a very important equation. It's not a fundamental in the sense that it follows from an effective equation, but in the limit of decoupling of frequencies, my Hamiltonian dynamics has generated a stochastic equation of motion with dissipation, fluctuations, and fluctuations are related by dissipation by a correlation function and this is called the fluctuation dissipation theorem. This is actually quite important, and this equation here is called the Langevin equation. Okay, so this completes our derivation of how a Langevin equation, stochastic differential equation of motion, which is not any longer time irreversible and contains stochastic terms, follows by assuming coupling with the bath and incomplete knowledge to the bath, and assuming that the bath has a dynamics that is much faster than the dynamics of the system, which leads to loss of memory, which is instantaneous. Averaging over our lack of knowledge of initial conditions generates a theorem that relates the thermal properties of my bath that is considered in thermal equilibrium, physical hypothesis, to the type of fluctuation it induces on the particle, through a theorem that is called fluctuation dissipation. We will see in the rest of this course that this theorem comes over and over and is very important to understand how a system reaches equilibrium starting from a non-equilibrium configuration. But we will dig on that implications in the next lectures. That's it for now. We will review this material again at the beginning of the next lecture. Goodbye.